start recording, and if you would like to not be seen in the recording, go ahead and switch your video off. I'll wait for you guys to do that. And just as another reminder that all attendees today are going to be muted, so if you have any questions during the webinar, go ahead and just write them in the chat box. We will be taking a select few questions during the presentation, but most of them will be saved until the end for a Q&A. And if you haven't already, make sure that in the chat box you switch the chat to field to all panelists and attendees or everyone so that everybody can see your questions. So that it's not set privately. You can find a link to the survey that I am going to put in after I stop sharing my screen with you. I'll put it in the chat box, and the survey is basically just a way for us to get your feedback from our webinars and see what's working, and we would just really love to hear from you. So I'll copy and paste the link in the chat box so you can check that out. I'll also be following up after the webinar with the link. Yeah, and so also just if I haven't said it already, the recording for today's webinar will be available on our website, and I'll also make sure to send you all the recording via email along with the survey link. So I don't know if I've missed anything, Sally. Maybe you can fill in the blanks. Otherwise, sure. I'll let her take it away.
So thanks all of you for participating in today's webinar. We've got quite a group, and that is wonderful. I am Sally Loomis. I'm the Executive Director of Hilltown Land Trust. And Hilltown Land Trust is a nonprofit organization. We were founded in 1986 as an all-volunteer land trust. And since then, we have conserved about 5,000 acres of land on 45 properties in our 13-town region. We are an affiliate organization of the Trustees of Reservations. And that partnership allows Hilltown Land Trust to focus on the core of our mission, which is protecting and taking care of protected land. And it gives us administrative support from a larger organization that's committed to the region. Public education and engagement events such as this one are a really important part of our work, and we are able to do much of this public outreach work thanks to the TerraCore program. Allie, who you just heard from, is one of our TerraCore members, our community engagement coordinator, and that TerraCore program provides us with 2 people each year, an engagement coordinator and a land steward, who really help round out the staff of this organization. We have 2 part-time staff and 2 TerraCore members. We are able to protect land and organize events like this thanks to the generosity of our members and donors. So if you're a member, thank you very much. If you're not yet a member and are able to be or able to give today, we'd love your support. I will be putting a link to our donation page in the chat box. This is a challenging year for fundraising for us and a number of organizations. We've lost a lot of revenue because our in-person events have been canceled for the bulk of the year. And we need additional support to be able to continue offering the programming we can do online and continue to protect land. Volunteering is another important way to show support for an organization such as ours. We're always looking for volunteers to help with our stewardship activities and to help with events and other work. I know many of you on this webinar have volunteered for us, and thank you. And if you're interested in doing that, please also be in touch. Some of you probably get emails from us. They contain lots of information about our events and what's going on with the organization, and we don't overwhelm you. So sign up for our email list if you're interested, or follow us on Facebook or on Instagram, and you can be up to date on the latest happenings with the Land Trust. I now want to take a few minutes to introduce our speaker, Tarin Weiss. So Dr. Weiss is a professor at Westfield State University. She teaches courses in science education, geology, and physical science, and her interests focus on sedimentary processes and stream flow and how students learn science. She serves on the executive committee of the National Association of Geology Teachers and recently has presented at the Geological Association of America's annual conferences and CERC. Now, you're going to remind me what CERC says. CERC is a program of Carleton College, and she has presented at their environmental geology workshop. And she's also published in the Journals of Educational Action Research and Science and Children. So with that, I will turn this over to Dr. Weiss, and we can hear about geology of the area.
All right. Well, welcome everybody. Thank you for joining us on this lovely day. In a perfect world, we'd be all standing on top of Mount Tom here, where you see this view painted by Thomas Cole in 1836, looking kind of northwest at the Oxbow. And today I'm going to try to summarize for you the geologic history of Western Massachusetts, and we have to include Eastern Mass in this, so we got to bring them in. So you get a sense of why the bedrock, the rock of our region or wherever you are, looks the way it looks, how it formed, and the effects, a little bit about the effects of climate and the most recent glaciation on the rocks that we see. You were asked to bring a rock with you today, and if you did, I will be holding up some rocks. In a smaller crowd, we could have had a little more discussion about the rock you brought and help you understand what you have. At the end, if you want to hang out, I'm happy to help you identify it a little more. But maybe you'll see an example that I hold up that matches what you have, and we can hopefully help you learn a little bit about the rock you brought or the geology of your region. So to begin, I'd like you to take a look at this bedrock map of geology of our state. We have about an hour, so we're not going to be able to make this too much of a discussion. But as you look at this image, what I would ask you to do is look for any patterns that you notice in this example map of the bedrock geology of Massachusetts. And when we say bedrock geology, we're talking about the solid crust. If you could dig away, get rid of all that pesky vegetation and soil, and just see the hard crustal rock below you, you would come upon rocks of these different types. Now, they're not really these beautiful colors. These colors represent either individual rock types or what are called formations, so combinations of rocks that formed through similar processes at a similar time. So as you're staring at this, maybe a pattern you noticed is that a lot of the rock types look striped. They're running up and down, north to south, and that's called the strike of these major rock formations. So if you start on the western side of the state, and a little crazy over there, but essentially you still see a north-south patterning. Keep going, but then right here in Eastern Mass, you start to see the rocks striking to the northeast. And so we know something is going on that's causing the rocks, as they appear at the surface, to have this, this striped pattern, whether it's due north-south or northeast. And this is the story that's going to help us understand how Massachusetts formed. And so what I'd like you to look at right now with these red lines is the way we break up Massachusetts into its different, what are called terrains. Terrains are actually hunks of crustal rock that have either sutured themselves onto Western Mass, like the Merrimack, Neshoba, and Avalon terrains. They came from somewhere else and actually smashed into Western Massachusetts. And that collision affected the rocks of the whole region because it increased the pressure and temperature and created a lot of rocks we called metamorphic rocks. So we can see here that if you're in Western Mass, you're sitting on this ancient rock that is part of the central core of North America. But these terrains are called exotic terrains, and they came from different places away from our Western Mass region. And they're similar to how you might picture Japan or Indonesia, and imagine those land masses on plates moving and colliding with Western Massachusetts. So we'll come back and look at this map again at the very end of our presentation. I'm not going to really spend time on this slide, much as I love understanding the bigger history of how we came to be. However, we are looking here at a solar nebula, the theory that our solar system began forming about 4.6 billion years ago, and through a process of gravitational attraction and accretion, rings of matter accreted into baby planets called planetesimals, and eventually this image follows just the Earth evolving over time into the Earth we recognize today at the very end of this image. So if you're interested in this, there's lots of great information online that summarizes the processes that help to form the Earth as we see it today. The one thing I do want to point out before we move on is this picture right here is showing us our Earth forming a nice spherical shape. Gravity has pulled this hot molten Earth together. And we started with an Earth that was very mixed up. Think of that periodic table of the elements, and 92 naturally occurring elements, and the heavier ones sinking to the center, forming the core, and the lighter elements floating to the crustal material, that outer layer. And so we're really going to focus on the lighter elements of the crust in this presentation. So I do need us to think about the crust to understand a plate, to understand plate tectonics. So a great way to think about the crust of the Earth is to think of an egg. And the reason it's not a perfect analogy, no models are perfect in science, is that if we think about the crust of the Earth as being cracked, as you see my egg here is very cracked, each crack somewhat represents a plate. And then if we go under that crustal material, we get into the mantle, which might be the white part of the egg, about 1,800 miles of solid, dark rock, and then the inner core, which is mostly metallic material. So it's this crustal material that we want to be thinking about today, and it's rigid and it fractures easily. And this image here, our crust is this brown layer at the top. And here's our mantle, and here's our core. And you're also seeing something really important to understand Massachusetts geology, which are these convection cells, where hot material can slightly start to flow and move up through the mantle to the crust, can crack the crust. That crust can move and eventually sink back down into the mantle at another boundary. So that's similar to me putting, hope you can see this, if this is my melty layer in the mantle, and here's a piece of crustal rock, as the melty layer moves, my crust moves along with it, on top of it. And so when we talk about plate tectonics, we're talking about the movement of crustal material over this asthenosphere, which is a little more like silly putty, and it can flow along with these convection currents. So we're talking about plate tectonics. Well, what is a tectonic plate? So again, just a little background, or probably review for so many of you. But if you take a look at this image, it might help you make some sense of that. The light brown color up here is land. So we call that continental crust. Averages maybe 20, 25 miles thick, thicker in mountain range areas, and thinner in coastal plain areas. We also have crust that's made up of the ocean. So this is ocean crust, much thinner, only maybe about 6 miles thick. So that's the crust of the Earth. And attached to it is this upper part of the mantle. You see it, I hope you're not colorblind. I'm sure somebody is. This layer here in kind of a mauve purple is the upper part of the mantle, and it's attached to the crust. And this is the piece that moves over this more melted layer of the crust of the mantle, excuse me, called the asthenosphere. So when we talk about a plate, we're talking about the crust, continental or ocean, with this rigid part of the upper mantle attached to it. And as the asthenosphere flows, the crust moves along with it. So I'm going to show you another image that's going to look super busy, don't read all the words. Let's just concentrate on the various parts of this diagram that show us movement of plates. So the way we see that in this diagram is by looking at these little white arrows. And what you're seeing in this picture is a cross section. So just like I have my egg, right? And if I slice my egg in half, you're seeing a cross section of my egg, the inside of my egg. So we have now sliced the earth in this picture. So you're looking at a cross section, almost like cut a piece of cake. And in this image, the lithosphere, the plate, is the gray. And you're seeing the ocean on top of it and land on top of it. And I just wanted you to understand, looking at these arrows, that plates are moving in 3 major ways. They're either moving apart from each other, called a divergent boundary. Sometimes plates are colliding with each other, and you can have a subducting plate right here, where one plate goes beneath another plate. And you can have plates that actually slide past each other. We do have some evidence of that in Massachusetts, but I'm not going to focus on that in this presentation. So we're really thinking today about plates that collide with each other and plates that move away from each other. The plates of the Earth, there are 12 to 15 major plates, many smaller plates. They're not even all shown in this diagram. They're outlined in this map with these red lines. So these are the boundaries between the plates, and the plates are named in black here. We are on the North American plate, and let's look at the arrows. So our plate seems to be moving west. This is the middle of the Atlantic Ocean, where plates are sliding apart in divergent boundary zones called the Mid-Atlantic Ridge. And so our plate is being pushed to the west. Over here in California at the San Andreas Fault, our plate is kind of sliding to the southwest. Not all plates move at the same rate of speed. They tend to move about as fast as your fingernails grow. Although, say down in New Zealand, there are parts of plates that are moving 24 centimeters a year, like super fast. So they don't all move at the same rate of speed. They're not all the same size. So we're still a little confused by this. People who study tectonics can't explain everything yet about why plates are different sizes, why they always move at different speeds, etc. But again, here we are currently, and we're on what's called a passive margin of North America. We're not near a plate boundary currently, but we used to be. So it's really the story of plate tectonics and changing climates that created the long and unique history of geology that's represented in Massachusetts. We have very old rock in Western Mass, billion-year-old rock, out in the Berkshires, and we have very young products of geology shown by the glacial sediment that's 15,000, 11,000 years old. So that's quite a huge span of time. So geologists have a lot to look at in Massachusetts. And the story of our geology is really the story of 3 supercontinents. Rodinia, Laurentia, and Pangaea. And I'm sure if we had time to chat about this, you guys, many of you would have said, oh, Pangaea, I know that, or oh, Laurentide, I've heard that word before. So we're going to focus as a timely manner as we can on these 3 supercontinents, and then how they affected the rocks of our region. I'd like to start with the supercontinent Rodinia. Not many people have heard of Rodinia. It doesn't get as much press as Pangaea. It formed about 1 billion years ago, and the cycle of supercontinents, on average, seems to occur about every 600,000 years. So yes, there will be another supercontinent predicted in the future. And oftentimes when you see maps of supercontinents, it's not always like at one point every piece of continental material was in one place. So it matters what map time you pull out. I chose this map, which is showing most of the land masses all together 1 billion years ago. And right in the middle, you see this continent it wasn't named at that point. All of this is Rodinia, but you see Laurentia, and that's one we're going to focus on very soon. So that continent formed about 1 billion years ago, and then it broke apart. And these green lines you see here show a huge mountain range that formed when Rodinia formed, because that collision created a mountain range called the Grenville Mountains, which ran up and down the East Coast and are over in Northern Europe as well, because that was part of the collision that built up the Grenville Mountains. In Western Mass, we have rocks that are still representative of that time, called the Tyringham gneiss, and in Monterey, Mass, for example, billion-year-old rock. And gneiss is a rock that looks like this. One way you can identify a gneiss is by this banding of light-colored minerals, mostly quartzes and feldspars, against darker-colored minerals. This tells me that this rock was put under a lot of heat and pressure. There must have been a tectonic collision to create a rock of this kind. So maybe some of you found rocks that have some characteristic like this. So perhaps some of you found a nice rock to bring to today's talk. Where would you find these rocks if we're focused on Western Mass? So I have a lot of maps in this presentation. I will try to orient you as best I can as we look at these. This is a clip just of half of the state of Massachusetts. You see the western edge of Massachusetts here, the New York border, the Tectonics and Berkshires over here, and the Connecticut Valley is here. So the rocks that are 1 billion years old, we find, let me show you one more map and we'll compare. We find them in this region, just west of this area called the Whitcomb Summit Thrust. It's this red region of, on this map that shows the Grenville rocks. And what this means is they were deep underground, but it's something caused them to be uplifted and then eroded away everything that was on top of them. And so these ancient billion-year-old rocks are peeking out of the peaks and the cliffs of some of the mountains in the Western Mass area. Well, eventually Rodinia is not here anymore. It must have rifted apart. And in geology, when we talk about rifting, we're talking about plate divergence. So we had a continent, Rodinia, and something caused it to break apart. And every time you break apart a continent, you create an ocean. So you can see here that a new ocean is being created as Laurentia, this northern continent, is moving away from this southern continent. And this happened about 650 billion years ago. And Western Massachusetts was sitting on this edge of Laurentia. And Eastern Mass, well, it doesn't really exist yet, but it starts to form as island arcs, like Japan-sized pieces of continental material that eventually make their way and collide with Western Massachusetts. So again, we had Rodinia, it breaks apart, and now Western Mass, kind of the New York, Massachusetts border, is sitting on the edge of Laurentia. Would have been a nice place to visit back then. We're at about 500 million years ago at this point in the Cambrian. There's no life on land. However, the oceans have ancient Paleozoic life. Animals with hard parts are just starting to develop, animals with teeth and bones. We have unique plant life at this time as well. And it was this beautiful sort of carbonate ocean, warm, clear seas. And off the coast of Western Mass then were sands and limey muds that eventually formed rocks called sandstones and limestones. And I don't know if any of you would have found a sandstone or a limestone unless you were in specific regions of Massachusetts right now. But here's a sandstone. If I rubbed it, I would have sand falling off of it. And here's a gray, boring limestone made of calcium carbonate. If I collide something into these rock types, I can change them. I can metamorphose them into two other rock types called quartzite and marble. So Western Mass, the Berkshire regions, are full of quartzites and marbles because future collisions changed those sandstones and those limestones into these new metamorphic rocks. And this gives us today the caves of Western Mass, because calcium carbonate material easily over time will dissolve and create caverns and caves. So some of you maybe have been cavers and been to some of these caves. I've got sand all over my keyboard. These caves in Western Mass, such as Crystal Cave, Pothole Cave, Baker's Quarry caves. And they exist there because limestone existed there and marble exists there. And that material weathers easily, dissolves easily, and creates caverns in those regions. I want to go back real quick to a point on this slide that were 500 million years ago, but I wanted you to notice these island arcs, these Japan, Indonesia type landmasses that are starting to move to the west and will eventually collide with Western Massachusetts. So the collisions are what the big story now of this presentation is, where we're looking at microcontinents colliding with Western Mass. And over here, here's another map. Western Mass is sitting on this edge of Laurentia, and Baltica eventually collides with northern Laurentia, and these land masses way down here off of Gondwana start moving through subduction zones, closing this old ocean and colliding with Laurentia. Eventually, by about 300 million years ago, we formed that supercontinent that many people have already heard of, called Pangaea. So let's think about that in cross-section. So I'd like you to sort of wrap your brain around this. Again, let's cut the Earth like we cut an egg, and you're looking at a cross-section. And there are 3 plates in this picture. There's, I have 2 images for you to view. 1 and 2, and let's focus on image 1 right now. So we're forming Pangaea through convergent tectonics. Plates are colliding. Here we have the northeast seaboard, maybe Massachusetts. There's a subduction zone off the coast, which is creating a volcanic chain. There's a plate that's just ocean, with ocean sediment here in light blue. And here's this island arc, think Japan. And everything is being pulled together to give us this bottom image. And I've mixed up the ocean sediment here to show you that it gets part of the mix. You see the land is raised up, and any rock types that existed before the collision have now been metamorphosed and changed into a whole suite of beautiful, beautiful metamorphic rocks. So this is the process that happened over and over again for a couple 100 million years to form the supercontinent of Pangaea and to build out Massachusetts to, well, even bigger than how we see it today, actually. So in this image, you see ocean sediments in blue that were pushed onto the land between the continent in yellow and the island arc on the right side. The maps that you're going to see in the next series of slides were created by a professor at Arizona State University named Ron Blakey, and he looked at the geology of the world and created these beautiful maps over time to give us a sense of the land masses, elevations, and where the ocean existed. A lot of the changes that you're going to see in ocean level are responding to elevation changes because of raising or lowering the Earth's surface, and climate changing over time. We're not going to talk too much about ocean levels, but I do think it gives you a good indication that even though here are all the eventual states in North America, a lot of them were underwater for a very, very long time. So after that original collision of Rodinia, it split apart. We have 3 more collisions that we need to talk about to form Pangaea. And the first is the tectonic orogeny. Many of you have heard of the Tectonic Mountains in western Massachusetts. They were the result of a collision with an island arc with Western Mass. They got maybe as high as 10,000 feet at one time. And any existing rock or ocean sediment changed from sedimentary into metamorphic rock at that time. So we may have had a mudstone rock called shale that can metamorphose into, I don't know if you get the shininess here, but into a metamorphic rock called phyllite. With more heat and pressure, you could create schist. So many of you know of the Goshen schist out here. And with even further metamorphism, you can once again create this super hard metamorphic rock called gneiss. And you also get a lot of granites forming at this time too, because deeper down in these collisions, the rock melts and crystallizes into granite type rock. So the rock of Western Mass from the tectonic orogeny, from the collision of that island arc, created rocks of this type. So I still have sand on my keyboard. We're talking about the tectonics, which run right along. Here's another map. Here's Massachusetts, Western Mass, New York border right here, and you're seeing the rocks of the tectonic orogeny here. And that's that first collision to start building out Western Mass from west to east. The classic view of the tectonics and the Berkshires here, we're on the top of Mount Greylock. It's made of rocks from the Ordovician period, and the rock really that makes up most of Mount Greylock is this rock called phyllite, metamorphic rock. And the resistant rocks that you see, the hills of the Berkshires, are really the result of these highly resistant metamorphic rocks that formed. And a way to also think about the ridges of Western Mass, and I know I'm really small and I don't know how well you can see this, but I'm gonna put some pressure on my napkin here, and you should be able to see the ridges of Western Mass forming. Oh, we got one big ridge. I can't hold it appropriately. So these collisions raise up the bedrock. They fold it and raise it up, and we have the striping, that north to south striping in Western Mass as a result of that collision coming from the east and raising up, creating these north-south long ridges and mountain ranges in our area. So Mount Greylock sits almost 3,500 feet high, and many of you have been there. You can drive up there and hike up there. The Appalachian Trail runs over the mountain, and it's a beautiful, beautiful region, a highlight of the tectonics, sitting up there in North Adams, or Adams, yeah. Another evidence of the tectonic orogeny that some of you have been to are the potholes in Shelburne Falls. But the rock you're looking at, maybe you're looking at it and going, oh, that's nice, because you're seeing that banding, right? So that is rock that was volcanic, because this is rock of the island arc that collided with Western Mass. And you see that swirly pattern because that once igneous rock changed into a gneiss. So I told you there are 3 collisions to get to Pangaea. So here's our second one. It's called the Acadian orogeny, and continual island arcs were colliding with Western Mass. And you see more of them here, you see some here, and then way down here in the bottom of my screen, you see the little tip of Gondwana, the bigger continent that eventually makes that final collision. So we're back about 375 million years ago. We're building up the Appalachians, which if you were there at the time, they might have been called the Acadian Mountains, and they stood as high as the Alps do today. So evidence is they were maybe 14,000 feet high. Well, how do we know that? We know that because they eventually eroded and all that sediment washed away and built up huge deltas. For example, in New York, there's evidence of all that material that at one time washed off of the mountains of Western Massachusetts. So the Acadian orogeny explains the collisions of the Merrimack terrain, the Neshoba terrain, that was that weird one that was a little more to the northwest, and the Avalon terrain, which is Eastern Mass, the Boston region, and south into southeastern Massachusetts is the Avalon terrain. And that collision took quite a long time to occur and build up the mountains to be this high. And again, any existing rock was metamorphosed or further metamorphosed to create solid rock and lots of igneous intrusions, such as granite. So I'm just going through a few pictures here to show you that continual collision over time. And then some of the rocks as you might see them on the landscape. Here are some schist layers from Western Mass, some granite-like rocks. We see the minerals there of some dark micas, some quartz, some lighter micas, and probably some darker hornblende minerals in here, making up that suite of minerals that make up granite. Here is one of my students pointing out awesome quartz grains that get stretched and pulled as rock is folded and stretched in these collisions. This is up right off on Route 2. And then gneiss, again, you find gneiss and you know something bad happened there, tectonically speaking. High pressure, high temperature, deep underground, maybe 10 miles, 14 miles underground to get that kind of a change to rock, to create gneiss. The final collision to give us the Pangaea and to create the Appalachians and to build up Massachusetts is the Allegheny and Orogeny. Famous for the Allegheny Mountains in Pennsylvania, and occurring sometime around 325 to 300 million years ago. The final collision to give us Pangaea. We see that final effect when Gondwana itself collided with Laurentia and all the other pieces of plates came together. Once Pangaea formed, it existed for about 50 million years, and then it too began to break apart. So Massachusetts, this is probably a good one to see at that point when maybe some of those mountains were pretty high. And remember, weathering and erosion is always fighting the uplift from collisional tectonics. So mountains are rising and then they are weathering and eroding. And the crust is adjusting itself isostatically based on the weight of the mountains. So there's never just high and low. Things are always sort of settling to their appropriate level based on the density of the materials. But again, we're talking about mountains that were maybe as high as the Alps. I'll go back, let you enjoy the Alps for a moment. Would have been nice to see those in Massachusetts, but this is what we see. Still beautiful, definitely lost thousands of feet of material. And you also see a flatness to this because something else happened to really wear down the tops of these mountains. And we'll talk about that in just a minute. So here's Pangaea. It existed for a while, and then motion in the mantle, those convection currents, started breaking up Pangaea. So here's a little animation of that. And the reason it's important to focus on this is if you're in the Connecticut Valley region, you've got a whole other set of rocks that are so cool and so unique because of the breakup of Pangaea. Am I doing on time? Okay. So in this picture, you start to see tectonic rifting. And I want you to notice not just, oops, the area of Massachusetts where we start to see these rifts, these openings as the land started to diverge and split apart, but you see these rifts occurring up and down this region. So our basin, our rift that happened in Western Mass happened north of us, it happened south of us, all the way down in North Carolina. There are rifts that formed, and only one of them totally broke apart, and that's where the coastline of Massachusetts is, the east coast of America is where that rift really worked. We are in a failed rift. It tried to split here, but it didn't quite work. But you're starting to see early signs of rifting about 230 million years ago. And if you break a continent apart, you've created a low area, and that low area can fill with sands and gravels, and it can fill in with lava. As the crust thins, asthenosphere material, mantle material, more melty material melts, makes it to the surface, and you can form lava rocks called basalt. So the rift basin is full of sedimentary and igneous rock that's 200 million years younger than the old rock of those earlier orogenies. So we're going to take a couple minutes and think about these basins, because maybe you live in one or you live near one. The basins of interest to us are the basin in the north, the Deerfield Basin. So say from Sugarloaf Mountain, Sunderland, north, the Pecumtuck Range, and then the larger Hartford Basin, which exists from little north of the Holyoke Range and Hadley, all the way down to the Long Island Sound. When you look at this picture, I want you to picture a flat area, how to do this with my hands, that pulled apart and created a basin. And into that basin flowed all the sediments and gravels over a very long period of time, with lava interlaying in between those sands and gravels. So this is a super unique area for Massachusetts. We don't have a lot of sedimentary rock, but we have it here in Western Mass. So there were multiple lava flows as the crust was pulling apart, and lava came up through various conduits called dikes. In places, 300 to 400 thick feet of lava overlaid the area, coming out of cracks or fissures. The basin filled with clay and sand and gravel. Those rocks created the sedimentary rocks we know of as, let me pull out a few, Arcos, sort of like, it's like I'm holding a pile of gravel here, but with sand holding it all together, and sandstones and shales, rock that may have formed in some shallow lakes that were in the area back at this time. And then, of course, again, the lava rock, the basalts. Here's a picture. I'm sure many of you have been here. If you haven't, please go. You can hike it or drive to the top of Mount Sugarloaf. You're looking south. Here's the Connecticut River, beautiful valley flowing towards the Holyoke Range. And you're looking at a range here topped with basalt. Some people think it's a volcano. It's not. It's a lava flow that was tilted on edge, and you're seeing the edge of it when you're looking at this mountain range. So you're looking at a flat lava flow that got tilted and is running east-west, and then the rest of the edge of it is running north-south all the way down, with all of those ridges that run through Massachusetts into Connecticut. And in between, we're seeing the whole basin of the, well, we're looking into the Hartford Basin here from the Deerfield Basin. Here's somebody on a field trip with us looking across the Holyoke Range, and way in the distance over here, we're back to that ancient Paleozoic, that ancient rock of the old Acadian orogeny, and we're looking at that dropped area that formed during the rifting. Okay, I don't usually put slides with a lot of words on it, so I just wanted you to take a second and look at some of the names over here. These are the names of the rocks that formed in these basins. Well, this is the Hartford Basin. Sorry, Deerfield Basin people, I didn't want to put too much information up. But what I want you to notice is the word flow. We've got flow, flow, flow. These are the lava flows that interlayered between washes of sediment that came in, the New Haven, the East Berlin, the Shuttle Meadow, the Portland, sediment sands and gravels, lake layers that were interlayered with these lava flows. And boy, you can look up how much material filled this basin. Some publications will tell you 15,000 feet of material filled the basins. Some will say less. So it's really interesting and unique. It happened over about 20 million years of the basin filling, lava flows forming, and at the same time, dinosaurs were marching along these sedimentary fine layers of sandstone and shale in this region. So we had evidence of a couple dinosaur varieties from this period of time, the Mesozoic, starting about 210 So it's 200 million years ago, let's say. Coelophysis, a 3 to 4 foot tall dinosaur. Anchisaurus, maybe 6 feet tall. And the favorite of everybody, Eubrontes, who was about 4 feet at the hip. We have evidence for these dinosaurs in the footprints that we have found up and down on some of this finer grained rock that filled the basin. So here you see a footprint of Eubrontes here. Here you see evidence that there were lakes in this region, because here are ripple marks, just like the ones you see when you go to Cape Cod. So this is a fine-grained sandstone ripple marks. We've had raindrop impressions, lots of really wonderful fossil, trace fossils found in the rocks of this basin. Go to the museum at Amherst College to see just the most amazing collection of these rocks and their fossils. So here's my foot next to a Eubrontes fossil. And then I just wanted to show you a bigger sample of conglomerate rock. So like the Mount Toby conglomerate, which is just a big mud flow that came into this valley at the time. So lots of really interesting things to look at geologically. So the rifting continued until eventually we formed the brand new, young, spanking beautiful Atlantic Ocean. So here's the beginning of it forming. And I'll just keep opening, letting this image go so you can see the ocean forming. And again, we have a rift valley, western Mass, but the rift really happened over by Boston. And the ocean's getting wider. South America and Africa are disappearing. Europe is disappearing. And currently we are still moving further away. The Atlantic Ocean is still diverging in the center at the mid-Atlantic ridge. Now, you're starting to see a North America that looks a little more familiar than the one I showed you back in a billion years ago in Rodinia time. So we're getting you to about 50 million years ago here. And 50, 60 million years ago, that's a long time since the mountains formed. So there was a lot of erosion. So the landscape really weathered down more to what you see in this first diagram here. But it's a little hillier now, right? So there was an event that occurred about 10 million years ago, probably from activity in the mantle as North America was stretching, that rose up the landscape. And by doing that, you can now allow rivers to cut down again and create the Berkshires that we recognize, because before that, they were actually pretty flat. So this renewed uplift allowed river cutting to create and shape the mountains that we think of as the Berkshires today. And that plus glaciations have given us this very flat landscape with monadnocks sticking up out of them, like Mount Wachusett and Mount Monadnock, really resistant igneous and metamorphic regions that weren't easily totally obliterated by the erosional effects of time and glaciations. And it's at this time that the Connecticut River formed. It made its way from all these streams flowing in from higher regions, and it captured those streams and it flowed down through the softer, more easily weathered sedimentary rocks. Here's Mount Monadnock standing tall at the north end of this peneplain. So we're going to jump ahead here to about 3 million years ago, and there's a glacier. We're moving into the most recent advance of the Ice Age, called the Pleistocene or the Quaternary. I circled where we are in that picture. We are under the ice, about half-mile sheet of ice above us, higher if you go further north, as the Laurentide ice sheet melted almost the way you pour pancake mix into a pan and it just sort of spreads out. That's how the glacier advanced from north to south into our region. Began formally maybe about 1.8, some people call it 2.4 million years ago, and it ended around 11,000 years ago, with the furthest advance happening, this picture, about 20,000 years ago, and then started eroding back away till the glacier now remains up in Greenland, right? The ice sheet of Greenland. We're in what's called a passive margin. Nothing's tectonically happening anymore in our neck of the woods. The closest plate boundary we have is the Atlantic, the mid-Atlantic ridge off in the center of the Atlantic Ocean. And so we've had increased erosion. This glacier came through and just scoured away any existing plant life that was forming, and the clock was reset. But by doing all that erosional activity, it renewed our ability to see these ancient rocks, the core of those old Acadian and Alleghenian mountains and Taconic mountains. The centers of them are now visible to us, and that's why we can see that old Grenville rock or that old Paleozoic rock. And the glaciers left just piles of stuff everywhere, right? You live near a gravel pit, you have sand in your backyard, that's from the last glaciation. So here's a picture of that Laurentide ice sheet at its greatest advance about 20,000 years ago. I'm going to show you a slide, and you might be glazing over. Hang in there with me. And I just want you to understand that this isn't the only ice age that has ever happened on the Earth. So this starts 4.5 billion years ago when the Earth formed, and you go across to today. And then you take this era called the Phanerozoic and you blow it up 700 million years ago to today. So these blue regions are past ice ages. In fact, this one is called Snowball Earth when we think the whole Earth was encased in ice. Cool story, but not for this presentation. So we are in this ice age, the Quaternary ice age here. But again, I just felt I should point out to you, it's not the only time. But what you should remember is this is the period of time of Pangaea and Pangaea rifting, and there were no ice ages. So it was a very warm climate, sometimes called a hothouse climate. Dinosaurs really loved this weather. They're reptiles, right? Cold-blooded. So this was a perfect environment for the evolution of their species. We're gonna move this along and just go right here. So here we are today. We're with a landscape. We have the remains of these mountain ranges that existed a couple 100 million years ago. But you can just tell even from this satellite image of a fairly eroded and weathered down landscape. To another group of geologists, they want to look at the superficial geology. They want to look at all the sands and gravels and all the features left by the glaciers. And so this map is just showing you different kinds of materials dropped by the glacier. And the predominant image you should see, if you're not colorblind, is pink. All this pink. And this pink is represented on this map as till. So till is this unconsolidated, mixed up material dropped by glaciers in a lot of different ways and for a lot of different reasons. And it really covers the state of Massachusetts. You also see here some of these dark pink, which are clay material left over from ancient lakes that sat in our region after the Ice Age. So we're just going to talk about that a little bit. Here's some till in Massachusetts, light colored, mix of all sorts of unconsolidated material, very not well sorted superficial geology. So one of the most famous glacial lakes that we have in Western Mass is Glacial Lake Hitchcock. And you see it in my image. Let me get all the words up in case you want to read them. Starting way up here in Vermont, New Hampshire region, and this 200-mile long lake going all the way down to about central Connecticut. As the glacier melted, we can't imagine the volume of meltwater coming off this glacier. You know, sea level was about 400 feet lower back then. So all that seawater was locked up in ice, and now it's going to return to the oceans and raise raised ocean levels. We have evidence that this lake sat here for a couple reasons, but one of the best ones and most interesting are these clay layers called varves. And maybe some of you have been to places where you can dig this clay. You get a light layer and a dark layer representing a year. And we have evidence that that lake sat around for about 4,000 years on the landscape until it eventually drained from a dam that broke in central Connecticut. We also have evidence for this in sand deltas. This is a sand delta from Sunderland gravel, and all of this sand is from rivers that washed into Glacial Lake Hitchcock and just dumped all the material they were carrying. And then the water continued to flow further into the lake. So lots of evidence for Glacial Lake Hitchcock on the landscape. And that left more material for geologists to make sense of and recreate the geologic history of our region. Glaciers left a lot of other cool things that you guys see every day around you if you're in Western Mass or anywhere in Massachusetts, such as kettle ponds. This is Walden Pond, a kettle pond. Erratics, this is an erratic from my town called Tipping Rock. That we take elementary students to, and they can actually tip the rock when you're 8 and you can move a couple 100-ton boulder. That's pretty fun. Drumlins, which are little sand, well, pretty big sand hills that can form under glaciers as the glacier moves across material. This is not a great picture of an esker. They're way easier to see in drier places with less vegetation, but they're like snake-like features that move across the landscape from rivers that flowed out from under glaciers. And then probably one of the easiest things to see besides erratics are glacial striations. So if you're hiking along and you have a nice flat region, if you see scratches like a cat came and scratched the rock, you might be seeing striations from the glacier. Rocks are embedded in the bottom of the glacier and they scrape across the bedrock, almost like claws of a cat, giving us ideas, and people can map these and understand the directions that the glacier moved. And here we are in our time. We are in the Holocene, this epoch that began about 10,000 years ago. The climate has warmed. We're in an interglacial period. Glaciers are still up here, and barring climate change, in about 20,000 years or so, they should come back based on astronomical cycles. So our geology is this story of collisions, of rifting, and glaciations that give us the rock types that you see all around you. And it left us with an amazing state, beaches full of quartz and feldspar sands, rocky coasts of granite, hard, beautiful, crystalline, nice schist, granite, and basalt. We have mountains and valleys, glacial hills, and sediments, and we have fossils. I didn't talk a lot about fossils, except for the glacial footprint, dinosaur footprints in Western Mass. But in Eastern Mass, there are fossil plant fossils, insect fossils. So we do have lots of evidence of past life as well. So the things that we see in the state really represent this long story of change over a couple 100 million years, starting from really Rodinia, that ancient mountain range that was formed as Rodinia itself formed. And we're left with soils that are representative of the geology itself. So the state soil of Massachusetts is called the Paxton. And it's made of glacial till. It's very clay. It has granite, gneiss, and schist, which now you know a little bit about why there's so much of that rock mixed into the Paxton soil. And that is a soil that is well suited for agriculture. And that is all a product of geology and climate and organisms coming together to create the soils of our state as a result of our geology. So if we go back to this picture, now I know without names, and you may not really be sure which terrain you're on. This line right here represents sort of Brimfield, where Brimfield is here. And this is the Connecticut River Valley, right here, called the Triassic Volcanics. So it's Mesozoic material with volcanic rocks. The Shoba terrain, it's hard to figure out exactly on here where you would start, but you're heading all the way up to near Newburyport area. And then most of eastern Mass, you're in the Avalon terrain, and there's underneath the sands of the morainal material from Cape Cod is a little bit of Maguma terrain. And this area is the Narragansett Basin, which has some really wonderful Paleozoic fossils and coal seams down there. So I hope this gave you some idea of how the state formed and why we have such a wonderful diversity of rock and features. We've got orogenies that build up the mountains, weathering over time brought them down. Nice schist, phyllite, slate, quartzite, marble, granite rock. We've got thrust sheets, rocks that were thrust over other ones, creating our hills of the Berkshires. We've got monadnocks. And then we have this awesome rift basin with Mesozoic dinosaurs walking through the sands and the clays of that time. So I want to thank you for listening in. This is a weird way to interact. I would rather we were all out on a field trip together talking about these rocks and looking at them. So thank you very much. And if you have any questions, stick around and I'm happy to try to answer them for you. Thanks a lot.
Thank you, Tarin. This has been wonderful. You can either enter your questions into the chat box and I can try and manage them, or once we get through those, we can unmute people and allow things to proceed that way. It looks like we're getting a few questions in right now. From Matt, do you have any thoughts on how Purgatory Chasm formed?
There's a lot of debate about Purgatory Chasm. And obviously it's a water erosional feature that is the result of maybe a huge wash of water, whether it's from a glacial age or a different backup of water that flowed through there, I don't know. But what I've read about it is that even the local geologists who study that still can't come up with a clear explanation of Purgatory Chasm and exactly why it's there. So I don't have a great answer for you about that. And if you look up the ideas, you'll come up with 3 to 4 different explanations.
And yeah. Am I right that Purgatory Chasm is in southeastern Mass?
It's south of Worcester.
Yes. Okay.
Mm-hmm. Yep.
I think it's a state park.
Yep.
And then a question from Michael Leff. How would you distinguish the Hilltowns from the Berkshires geologically?
That's a good question. Geologically, I don't think, I think the Hilltowns is just more of a cultural distinction. Once you get out of the Mesozoic Valley, so like Northampton and north, you're at the edge of the Rift Basin. You are geologically, you're in a similar age rock, couple hundred, like 400 million year old rock that continues all the way out into the Berkshires. So they are different rock types. Like where I live, I'm in one kind of rock type, and a half mile up the road is another type of rock, but it's all still schist. So I don't think geologically we make huge distinctions between the Hilltowns and the Berkshires. It's more just elevation. So we call them Hilltowns. Yeah, that's my answer.
I have a question. In my land conservation realm, one of the factors that plays into a site's resilience to climate change is the underlying bedrock or geology. And do you know much about that?
Well, when we're talking resilience, do we mean like for towns to like the resiliency program that the state has set up?
So there's a lot of data put out by a few different much larger conservation organizations, such as the Nature Conservancy, in partnership with others, that looks at a lot of different factors that relate to the land's resilience to climate change. And there's things like microclimate and, you know, what direction is the slope facing, and how connected are, you know, looking for north-south corridors of open land or protected land for wildlife migration. But one of the factors in there is the underlying geology of the land. And I think it probably relates to the soils and the interaction between the bedrock and the soils. But, you know, it's just one of those things that I look at and I have to say, okay, because I don't know a lot about it.
Right, so geologically, in terms of geologic resilience for climate change, the soils issues is big. So if you have a lot of till, that can fracture and become a slurry and easily, you know, what we saw in Hurricane Irene, you get all that flooding and all those slope failures. And also when you have metamorphic rocks that fracture, they are easy to slide down. So increased flooding is going to increase lubrication between layers that form. So it's probably a mix of all you talked about, where they're weighing what type of rock. So so schist often, I'm going to combine two rocks, but schist often will fracture. And so if that is at a big angle and you have a lot of flooding, you can break off big pieces of that rock. So that is not a pretty resilient area.
Ah, interesting.
So it's probably a whole mix of things based on all the factors that you mentioned. Direct.
Yeah, and I think that's what, you know, it's a fairly rich analysis. So I think it is a combination of factors.
Yep.
Let's see, we have another question here. Are there any legal protections for areas if fossils are found or other geological features that are legally protected?
Well, yeah, so the dinosaur footprints, for example, that we see along in Holyoke, those are all protected. It's illegal to go in and dig them out because they're already in protected areas, like Nature Conservancy maintains, or trustees, I'm sorry, maintains that area. So if somebody has identified the land and it is formally protected, yes. You could go into your own backyard, or I believe even on forest land maybe, and dig up fossils and nobody's going to stop you. It has to already be protected, I believe. Yeah. So if you found a dinosaur footprint in non-protected land, you probably could keep it. Although if it's whoever the owner is of the property, they have really first dibs on it. Yeah, but it's not like what we've been reading about with the roundabout in Northampton. They don't have those same kind of protections as Native American artifacts. No.
Another question, can you say anything about the blue soapstone intrusion in Andover? I understand it's unique in Massachusetts.
So soapstone, we actually have some soapstone in Western Mass as well. In these regions where you have colliding plates, if you have, in some cases, if you're colliding certain kinds of rocks, like really dark rocks, like this basalt, soapstone is a metamorphic result of a collisional process between certain types of rock. So it's a metamorphic process that creates that kind of a rock. So it's telling you there was some sort of heat and pressure and collisional activity that helped create that rock. And it means that the rock itself, there was some unique minerals and things in that rock that allowed it to become soapstone.
Great. That is, I think, the end of the list of the questions that I have seen in the chat. And my apologies if I've missed some because it's a little challenging. If people have others and want to unmute themselves, we can take a couple more minutes. And Tarin, thank you so much for
you're welcome.
Talking with us. So I forgot to mention in the beginning, Tarin lives in West Hampton and has volunteered before for Hilltown Land Trust. And it's wonderful to have people like her in the community who can share some of their knowledge with us. And I guess the silver lining to some of this stuff happening now and not being able to do in-person events is that we've all got better at doing events this way. And a lot of us are learning a lot of new things.
Absolutely. Well, I appreciate being asked to share, and it's always a challenge to share all this stuff in this manner. So I hope people left with some understandings of what's going on.
Well,
Thank you very much. This was great. Thank you so much.
Thank you.
Yes.
Thanks for coming.
And thank you all for coming. Like I said, Hilltown Land Trust, we have a e-news that comes out once a month, and we have an active Facebook page and Instagram account, and we post information on upcoming events. We have something next Monday on virtual forest therapy. You can check it out, the description on our website. And if you're a member, thank you. And if you're not and enjoy events like these and have the capacity to support them, we'd love more support and more donations. So thank you to Tarin and all of you for participating.
All right, thank you very much.
Yep.
Thank you.
Oh, and we do have a survey that will be emailed out to everyone. There's a link in the chat box for the survey right now. If you just want to click on it and do it, there's no time like the present, but that helps us get feedback for future events. And that's always good.
Great. Thank you,
All right.
Tarin.
Thanks so much.
All right.
Bye-bye.
Bye-bye.